Hello there. For those who missed the lab on gravity and apparent weight, here's your recap. What we did in the lab, I used a Vernier force sensor and I hung a weight from it. It was an unknown mass. A free body diagram, which we started with, represented two forces on it because it was at rest. The object that was hanging on the force sensor, it was attached by a string. So we have a force of gravity. Remember, that's the formula for force of gravity, mg. And you are welcome to use mg to represent force of gravity or just use Fg. And then we had, instead of normal force, because remember, normal force comes from a surface, this was a string. So we marked it as Fs. And the reading on the force sensor attached to the string was 5.13 newtons. So that is the force of the string, and it is a weight of the object. A weight, we can use W for it. A weight, normally, if an object is at rest, is equal to the force of gravity in magnitude. Because if you have mass, you have force of gravity. If you are not out in outer space, and we are not, we are on planet Earth, we experience force of gravity. And any object in a classroom experiences force of gravity. It is attracted to everything that has mass, but mostly to the planet. So everything has this G that is on average 9.8 meters per second squared on planet Earth. Weight is the force that an object will apply to anything it is standing on, leaning on, lying on, or in this case it was hanging from the string. So that's the weight. If force of the string and the weight is 5.13, if I divide this by 9.8 using this formula, I will get 0.52 kilograms. And to practice, let's express this mass in grams as well. 1 kilogram containing 1,000 grams. Therefore, if we have 0.52 kilograms, that equals 520 grams. It's good to remember how to convert grams to kilograms because you will encounter those problems as you work on examples for this unit. Based on the knowledge of the first law, we discussed how if the object is moving with a constant velocity, or at a constant rate, up or down, doesn't really matter whether it's moving up or down, and I demonstrated it by moving it gradually and showing how the weight remained the same. If I moved it upward at a constant velocity, force of the string was still equal to force of gravity. The same happened when I moved it downward. So it doesn't really matter. So long as velocity is constant, it doesn't matter whether we move up or down. Because velocity is constant, forces are still balanced. And then we extended that to Newton's second law. What if I yanked the object with an upward acceleration, with a downward acceleration, or what if it started free falling? The hypotheses were that if we accelerate the object, yank the object with an upward acceleration, then force of the string, which equals the apparent weight, will be greater than mg. If it's accelerated downward, then force of the string, which is the apparent weight, will be less than mg. And then if it's free falling, remember what free falling is, it's a motion under the influence of gravity alone. Then if gravity is the only force acting, apparent weight is going to be 0. That I did not demonstrate so as not to damage the property. In different classes, my yanks were different and therefore the apparent weights were different. But for the sake of the exercise of those who missed the class and for those who were there but would like to practice one more time, let's suppose that the apparent weight with the upward yank was 1563 newtons. Then force of gravity is still mg, so it's downward, and if you remember, that was 513 newtons. 5.13 newtons, that, and remember, we always mark our forces with what they are, not just the values, but with what they are called, versus force of string or apparent weight, which is 15.63. In that case, the net force is going to be 15.63 minus 513. That is going to be 1050 newtons. Then the acceleration that was given to the object in the upward direction would be net force, which is 1050, divided by 0.52 meters per second squared upwards. use the calculator to figure it out on your own. When I allowed the object to slide down with an acceleration downward, then the apparent weight was less. And again, just for the sake of the exercise, let's say it was 0.63 newtons. Again, in different classes, we had different values. So 0.63 newtons. If we have that, then force of gravity is still the same. It's still 513 because it's the same object on the same planet in the same classroom. So gravity didn't change. The apparent weight changed. The force of the string, the apparent weight, now appeared to be 0.63 newtons. Then net force, in this case, is going to be force of gravity, 513, minus 0.63. So that's going to be 4.50 newtons. So the difference between the two forces, now the downward force, force of gravity, I forgot to label this, is greater than the upward force of the string or apparent weight. And in that case, your acceleration is going to be 450 over 0.52 meters per second squared downward. And then the backside of this worksheet was based on this, but you were asked to figure out the apparent weight based on the acceleration. And if you need help, there is a link to the video that walks you through that as well. Keep learning. See you in class.